I'm going to record this and make it available later. At least I should. If for some reason you look for something and it's not there, like the notes that I wrote down on Monday, please remind me and I'll make sure I make those things available. Okay, before we get started, I want to kind of look at what we're going to be doing in the near future in terms of test dates and whatnot. Now, we probably did this last time, but that's how bad of a short-term memory that I have. Did we kind of forecast when the next test is going to be? And that was 27th. Oh yeah, that sounds familiar. Okay. Sorry, the microphones keeps brushing up against my stubble because I didn't shave this morning and it's making a scratching sound. All right, so test 2 is tentatively, that's a Wednesday, right? Wednesday, October 27th. That would be 3 weeks from today. We're fine. Okay, I was like, no, it's next week. No, that's a different class. Okay, first things first. Does anybody have any homework questions they'd like to ask about from 3.2, understanding and interpreting confidence intervals? Which one? 68. Okay. All right, the one about soda consumption and mortality in Europe. Okay, I'm going to attempt to do something. Folks in Zoom, you're not going to see the things I'm clicking real quick, but I'm going to attempt to find the same question in the previous edition so that I can put it up on the screen for everybody to see. My files will go to last fall. We'll go to this class. We'll open up the, there it is, the textbook. And in this book, it's on page 245. If I add 20 to that, that's 265. I should be in the right neck of the woods. I overshot it a little bit. 3.3, 3.2, here we go. Here we go. And it was the question about soda consumption and mortality, which was about number 68. Let me share the screen with the Zoom folks so that they can see this now. All right, Zoom folks, I was just scrolling through this book. All right, I'm in the right neck of the woods. I am looking for soda consumption and mortality in Europe. I'm not seeing it. I'm seeing a lot of interesting things, but I'm not seeing that. Well, that's disappointing. I was hoping I could just copy and paste into the Zoom text box, and I'm not seeing that. So I'm gonna have to do a semi-decent job of typing things into here. All right, so we're gonna take a look at number 68. Let's see, number 68 on page 245. All right, I'm going to read it so that it's recorded on the Zoom session, but I'm clearly not going to type all the words. A hazard ratio quantifies how much greater the risk in one group. Let me try that again. A hazard ratio quantifies how much greater the risk is in one group relative to another, with a hazard ratio of 1 indicating that there is no discernible difference between the groups. A hazard ratio greater than 1 indicating greater risk for the first group, and a hazard ratio less than 1 indicating less risk for the first group. All right, so which of these things is more hazardous? And we'll come up with the ratio. A large study conducted in Europe examines whether higher consumption of soft drinks of any type is associated with an increased risk of death. In the study, the hazard ratio for mortality for people drinking 2 or more glasses per soda a day relative to those drinking less than 1 glass a month was 1.17, with a 95% confidence interval for the hazard ratio of 1.11 to 1.22. Now, I'm clearly not going to type all that. I'm going to type the relative information at the end. We had a 95% confidence interval. Is 1.11 to 1.22. Let me widen the text box here. And what we are estimating the hazard ratio of risk of death. If I can't spell death, I guess that's a good thing. Risk of death for drinking 2 or more sodas per day versus less than 1 per month. And I'll admit that the context of this, the concept of a hazard ratio might make this problem seem a little bit more difficult than it actually is. But there's the main setup. And the thing that I didn't capture in the Zoom session here is that if your hazard ratio is greater than 1, then the first thing is riskier. If it's less than 1, the second thing is riskier. And if it's equal to 1, they're equally risky. All right, so there's the setup. Now, did you have a particular question you wanted to ask? Okay, so part A. Can we conclude with 95% confidence that high soda consumption is associated with an increased risk of death? Justify your answer using the confidence interval. All right. So really, let me kind of summarize what it just asked there. In part A, it's asking, can we conclude that high soda consumption is associated with increased risk of death? All right, so let's think about what they're really asking. They're asking, is there an association between drinking more sodas and having a larger risk of death? Well, according to this confidence interval, we're 95% confident that this hazard ratio, whatever it is between these two numbers. And remember what it said in general about these hazard ratios, which I'm going to type in red in a slightly smaller font. What it said about the hazard ratios in this problem is if the ratio is greater than 1, that means the first, how they describe it, first group is more hazardous. I don't want to get too hung up on the hazard ratio concept rather than the interpretation of the results. If the ratio is less than 1, then not the ration. If the ratio is less than 1, then the second group is more hazardous. And they also said if the ratio is 1, then they're equally hazardous, because you're making a ratio of things, and if they're equal, then their ratio is always equal to 1. To answer the question, can we conclude high soda consumption is associated with an increased risk of death? Well, that was the first group. The first group was drinking 2 or more sodas per day, and the second group was drinking less than 1 per month. And so the short answer is yes. And the reason is we're 95% confident that this hazard ratio is in this interval up here. And every number in that interval is greater than 1. Since every number in this interval is greater than 1, we're 95% confident that this is the case. So we're 95% confident that the first group is more hazardous, meaning that we're 95% confident that it is riskier to drink 2 drinks per day, two sodas per day, than it is to drink less than 1 per month. Common sense would probably say that, but it's always nice to have numbers back it up. So to answer the question, it would probably be along the lines of this. If I can get this to do what I want, text box, we'll put it in black. And our answer is yes. According to the interval, we are 95% sure the ratio is greater than 1. And that would be sufficient to conclude that there is a pretty strong association with more soda consumption versus increased risk of death. Now, I want to show you when you would answer no. Okay. You would answer no if you were not 95% sure that this ratio is greater than 1. I'm going to come back to this page in a second. But just a hypothetical, if the interval were, let's say, I'm just making up an interval here, 0.83 to 1.09. We are no longer confident. Well, I'll say 95% confident. The ratio is greater than 1. Because that interval has values in it that are less than 1. So it could be, greater than 1. It could be less than 1. It could be equal to 1 because 1 is in that interval. So there would be an example where we could say, no, we're not confident that there's an association between the two. Or if all of the values of the ratio were less than 1, for example, if it were something like 0.75 to 0.91, then now we would associate the reverse, that the second group has a higher association with death, although it wouldn't make sense to say drinking less sodas is unhealthy for you and drinking more sodas is healthy. I don't think anybody would say that. But yeah, this question was the intent of this question, and I'm going back to the previous page. The intent of this question was to interpret the results in the context of the problem. And since 1 was the barrier between this group is riskier versus that group is riskier, and our confidence interval is completely greater than 1, then we're 95% confident that the ratio is greater than 1, which means we're 95% confident that there's a higher risk of death if you're drinking 2 or more sodas per day, hence an association. Okay, that's a good question. As far as part B, which says, can we conclude that increased soda consumption causes a greater risk of death? Is that not what I just said? I think I accidentally answered part D. And did I not answer part A? Can we conclude with 95% confidence that the high soda consumption is associated? Yeah, we can. Because all the values, it says justify your answer because all the values in the interval are greater than 1. That's the justification. Not really sure. I see the difference between A and B. Let me read A and B real quickly. See if you can pick up on the subtle but important difference between the two. A was, can we conclude that high soda consumption is associated with an increased risk of death? And B is, can we conclude that increased soda consumption causes a greater risk of death? Y'all hear the subtle difference between the two? The first one was asking if there was an association or a correlation, if you will. The second one was asking if there was a causation. So you know the old adage, correlation doesn't imply causation. So really, all we can really say without further evidence is it's associated with an increased risk of death. There's an association or a correlation, if you will, but that doesn't necessarily mean that consuming more sodas causes the higher risk of death. So, I mean, the difference between A and B was so stealthy, I even overlooked it for a moment. But A is asking, is there a correlation, basically? And B is asking, can we conclude causation? And the answer is no. There is a way, by the way, there is a way that when you spot a correlation, you can do further investigation to conclude causation. There is a path from correlation to causation, but you can't just automatically assume that if there is a correlation or an association, then there must be a causation in there. It must be that this is causing that. All right, so thank you for asking about that one, because that really kind of gets us back into the flow of things. All right, does anybody have any other questions on number 68 on page 245? No? Okay. Does anybody have any other questions they'd like to ask about? Yes, ma'am. I hope I can. Do you find solitude distressing? I'm going to try to find this question in the previous version as well, so that we can have a visual of it. Do you find solitude distressing? Let's see. Do you prefer pain over solitude? Interesting. Aha. Eureka, I found it. Do you find solitude distressing? All right, I'm going to share this so the Zoom folks can see it. I didn't want to share it if it was a bust, but it looks like it's the same question as this one. And I'm going to try to do as much zooming in as I can without losing any of the problem. That looks like as much as I can do. I should scan over it to make sure that it's pretty much the same. Do you prefer solitude? Oh, that's not it. I'm sorry. I got suckered into saying that's it. Really? Really? This is why you should buy the new edition. That was sarcasm. Okay, well, never mind. I thought it was in there. Okay. You know what I need? A PDF of the 3rd edition. I should see if I can get a hold of one of those. All right, so we're going to take a look at number 63. You said 63, right? No, 62. Oh, wait a second. Was that it? I'm sorry, I'm all over the place. Do you find solitude distressing? That was it. Okay. I'll get my head on straight here in a moment. All right, it was this one. Do you find solitude distressing? Looking for matching numbers, 10 minutes, 76, 146. Yeah, okay, this looks to be word for word the same problem as in the third edition. So this actually is your number 62. It just says number 58 up here. All right, was there, well, let's get into the context and I'll see if you had a specific question. All right, for many people, being left alone with their thoughts is a most undesirable activity, says a psychologist involved in a study examining reactions to solitude. In the study, 146 college students were asked to hand over their cell phones and sit alone thinking for about 10 minutes. Afterwards, 76 of the participants rated the experience as unpleasant. Use this information to estimate the proportion of all college students who would find it unpleasant to sit alone with their thoughts. This reaction is not limited to college students. In a follow-up study involving adults ages 18 to 77, a similar outcome was reported. And the questions are: give notation for the quantity being estimated and define any parameters used. Give notation for the quantity that gives the best estimate and gives its value. Okay, is there a particular part of this problem that you wanted me to clarify? Okay, well then let's talk about the whole problem. All right, I'm going to copy and paste the questions into Zoom. I'm not going to copy and paste, well, maybe I am. I'm not going to copy and paste the entire problem because I just want to focus on the questions. All right, let's go back to the whiteboard, open up a text box, and hooray, it copy and pasted. Okay. All right, so we're going to do these things, and let me put some space in between so I can write some stuff. All right, so let's talk about how to dissect this. When you're asking to give the notation for the quantity being estimated, two things should pop into your head. Number one, when you estimate about a population. You don't estimate about a sample. You measure the sample. You estimate the population. So we're being asked for a quantity about a population, which means it's going to be something like mu, p, sigma, or any of those other population parameters, and define any parameters being used. When they say define any parameters being used, they're asking you what is it you're measuring. So let's go back to the problem and see if we can figure out which population thing I'm measuring. And as we do this, I want you to think about the question being asked of these students and whether the answer is quantitative or categorical. Let's go back to the question. All right, so what were these students, what do you think these students were asked? They sat alone with their phones for 10 minutes, and afterwards 76 of the participants rated their experience as unpleasant. So what question do you think they were asked? It's practically highlighted. Was your experience unpleasant? Or how was your experience? Something like that. But regardless, they asked a question whose answer was not numerical. Was this experience unpleasant? 12. That doesn't make sense. Their answer was yes, no, or rate your experience, pleasant, unpleasant, horrific, tolerable, enjoyable. I don't know about you, but I kind of appreciated the Facebook outage Monday. It was Monday, right? Okay. It's like, oh, good. I don't have to worry about that. But regardless, the question that was asked was categorical in nature because the answers were non-numerical. Was it unpleasant? Yes or no? How did you feel? Unpleasant, pleasant, whatever the question was, it was non-numerical. So if we're going to measure the results, so to speak, we can't find a thing like a mean because there are no numbers to average, but we can always ask the question, what percent of them said something, or what proportion of them said something? Remember, proportion is just what fraction or what percent of a group has a certain characteristic. In this case, the characteristic of having an unpleasant experience. So if you can process all that, that number one, we're talking about a population, and number two, because we're given information that could build a proportion instead of a mean, the answer to this question is P. And that is the quantity being estimated. And what is it that that represents? Well, I'm going to type this because it'll be faster and easier to read. In fact, I'm just going to type P equals over that. So I'll erase that underneath it in just a second. P equals the proportion of, now we got to figure out what population we're trying to estimate something about. So let's go back and see where this sample came from. In a study, 146 college students. Because all of the sample were selected from college students, that's the population that we're trying to figure something about. So go back, please. Let me get rid of this P equals right there. Well, I didn't mean to do that. Get rid of you, get rid of you. Oh, the joys of doing, fine, be that way. All right, P equals the proportion of all college students who felt unpleasant. I'm not sure that's the best way for me to say that, but it's how I'm going to type it. Felt unpleasant when away from their phone. And you could just hijack the words directly from the problem to describe this population, or excuse me, the proportion and the population that we're selecting from. But that's all they wanted for part A. What variable are we trying to estimate about the population, and what is it measuring? All right, any questions about part A? Okay, part B is to give the notation for the quantity that gives the best estimate and gives its value. Now, when you see the phrase best estimate, I think I told you how you should interpret that before. Does anybody remember what the phrase best estimate is really code for? Gee, I'd like to estimate this value for the population, but we can't measure populations well, but we can measure samples. Whenever you see the phrase best estimate, the phrase best estimate is a key phrase. Well, let's just put it this way. Best estimate basically means a sample measurement estimating the population parameter. So in other words, if we're going to estimate population proportion, our best estimate is a sample proportion. What is the variable for sample proportion? P hat. If you did not know that instantly, that needs to change. I'm not above giving a pop quiz at the beginning of class one day, asking you to match names to variables. And I mean like a 5-minute, get it done and get it over pop quiz. That's not so subtle. That's not a very subtle hint as what you might expect in the near future. All right, so P hat is the sample version of the population parameter that we're estimating. P hat would be the proportion of the sample of college students who felt unpleasant when away from their phone. It was out of 146 college students, 76 rated the experience as unpleasant, excuse me. In retrospect, it's actually a pretty straightforward and fairly easy question once you understand what the question is. What variable about the population are you attempting to estimate? Proportion of the population. What sample variable estimates it? P hat. What's the value of P hat? 76 over 146, which we could turn into a decimal, excuse me, or a percent if requested, but that would suffice. Okay, so any questions on part B or either part of this? Is there a part C? There very well could be. There is a part C. And was it not on the, was it not here? Was it just, did I just not see it? Oh, let me guess. Not only is there a line break and a column break, there's a page break between part B and part C. That's just bad formatting / editing on the editor's behalf. That is a problem that was fixed in the 3rd edition, though. There is a part C. So let's take a look at it. What I really wanted to do, though, is make note that this is question number 62 on page 244 in black and larger font. Okay, but there is a part C. Thank you for asking. Paste. Thank you. Give a 95% confidence interval for the quantity being estimated, given that the margin of error for the estimate is 8%. All right, so a few words here that need deciphering. Draw, please. The quantity being estimated, I can't stress this enough. You estimate things about a population. You measure things from a sample. So the quantity being estimated is again referring to a population value. We're estimating P. So what this is really saying is we are trying to make a confidence interval for P, specifically a 95% confidence interval for P. Now, why is it important to know what you are estimating? Because when you make a confidence interval for a population value, it is always centered at the best estimate. In other words, this interval is going to be centered at the value of P hat. It will be centered at the value of, now I can't type a hat, but I can type that, P dash hat. It will be centered at the value of P hat. And notice that our margin of error is given as a percent. Margin of error is 8%, which means that we should also think of P hat as a percent. Back in part B, we weren't told what to do with the value of P hat, so I just set up the fraction and said, I guess that's good enough. You didn't ask for more, except now it's asking for more. P hat was 76 over 146. Can somebody do me a favor? Divide it, move the decimal 2 places, and then round that answer to 1 decimal place. It should be a little bit less than 50%. So it's going to be 40-something point something percent. That's what I'm looking for. Am I going to beat you to it?
I think it's 52%.
It's 52%. Oh, it is more than 50%. Yeah, you're right. My estimation skills were a little shoddy there. It is not less than 50%. It's more than 50%. In case you're wondering, somebody on the Zoom chimed in and spoke in my ear. I'm not just hearing things. 52, and if we round it to 1 decimal after that, it's 52.1%. Okay, so that's going to be the center of our interval. But remember that to make an interval, the interval is by definition the center, which is P hat, plus or minus the margin of error. So we need to figure out 52.1% plus or minus the margin of error, which they gave us is 8%. So all we have to do is subtract to get one number, add to get the other number, and there's a couple of ways to write this result. One way is to say from the lower end to the upper end. That's an R, and that says from. Sorry, my OCD won't let it go. If we subtract that, we should get 44.1%. And if we add, we should get 60.1%. Now, you could also write this in a set of parentheses. It's kind of borrowing from algebra where you write an interval of values by putting them next to each other with a comma. Oops, that percent was supposed to be inside. I actually prefer the words. I would accept the other one, but I think the words are a little bit more descriptive, because if you don't know the context, you might not know what those 2 numbers at the bottom are trying to say. So we would say, I'm 95% confident that the percent of college students who would have an unpleasant experience in this experiment is between 44.1% and 60.1%. All right. Any questions about part C? Okay. Just a heads up, the rest of this chapter is essentially about building confidence intervals, which is really easy if you have the center and the margin of error. The trick is coming up with both if they're not just given to you. All right, I've got 439 right now. So what I'd like to do is go ahead and move on to the next section. And if you have any further questions from this homework, just contact me outside of class. Real quick though, concerning a quiz over this homework from 3.2 and possibly from 3.3. There will be a Canvas quiz. I can't promise you it will be ready by Friday. In fact, I don't know if they were ever actually ready by Friday, but I know if it's not ready by tonight, and I'm pretty sure it won't be, then it won't be ready until Tuesday of next week, excuse me, Monday of next week. As I mentioned to everybody at the beginning of the semester, there's a day that I won't be here, and that day is coming up this Monday, October the 11th, I believe it is. I could possibly make it back here in time. Not that it is super important why I'm gone, but so to repeat and resume recording, the quiz over this homework from 3.2 and possibly 3.3 will probably not be available until Tuesday of next week at the earliest. Does that mean it'll still be due on Friday? Well, I'll be honest with you. Doing the quiz shouldn't take too terribly long. And if you can't do it in 3 days, what's the difference between giving you more time than that? I mean, I think it's reasonable to ask you to have the quiz done by Friday, because you'll still have a chance to come back to class Wednesday of next week, ask questions, and go in and finish that quiz. So I'm going to maintain the Friday due date just for consistency, even though I know that this quiz won't be ready to go until Monday night at the latest. I really want to get it done Monday night so that I can get that out of sight, out of mind. And if you're wondering, why don't you just write the quiz? Trust me, writing the quiz is not just a matter of typing things. It's making sure the questions are formatted correctly, making sure that you get the correct number of questions that I want in case it's a random selection, and test piloting the quiz a couple of times to make sure that it's doing what it's supposed to do. It takes me a good couple of hours to put together a quiz. And could I do that tonight? Yeah, between when I'm packing and making sure that I have your videos ready for next Monday, because that's really what I'm probably going to be doing tonight, is making videos for the content from Monday. Okay, let's move forward. That's a good direction to move. All right, so we are going to go ahead and begin the next section, 3.3. This is kind of a little tricky one to wrap your mind totally around. And I say that because for me, it's a little tricky one for me to wrap my mind totally around. I get the idea, but knowing, it's called constructing bootstrap confidence intervals. But knowing where we're going eventually, in the future, we'll look back on this and go, oh, that was kind of there, and we did it, and we're not doing it anymore. So it's kind of like a building block towards a larger goal. So let's get through it. All right, so what do I mean by constructing bootstrap confidence intervals? Well, recall that you need 2 things to build a 95% confidence interval. The first thing you need is a center to build around. That's pretty easy. It's just some sample measurement. I'm going to take the font size down for a minute so that I can fit more on this page. I hope that's large enough that everybody can read it, especially towards the back of the room. Folks in the back, is that large enough that y'all can read it? Okay, just want to make sure. You need 2 things to build a 95% confidence interval. Number 1, you need a center to build around. Well, that's just the measurement that you get from your sample. You want to estimate population mean, take a sample, calculate its mean. You want to estimate population proportion, take a sample, measure its proportion, or any other thing about the population that we're going to estimate. But the other thing you need is a margin of error. But for a 95% confidence interval, And from this point forward, for the sake of time and brevity, I'm going to type CI anytime I mean confidence interval. Y'all got that? So nobody's going to ask me, what's CI? It's confidence interval. For a 95% confidence interval, we know that the margin of error is 2 times the standard error. There were too many letters in a row there. Margin of error is 2 times the standard error. So really, we need the standard error. Where does it come from? Well, this is what's bugging me. I know the answer to that. The answer is in chapter 6. I accidentally showed you one of the answers earlier when we started this chapter, but for now, let's pretend I didn't. Where does the standard error come from? Well, considering that when we mean standard error, we mean for the entire population. We can't measure that because if we could, then we could measure the entire population and not have to estimate a thing. So we seem to be in a catch-22. In order to build this thing to estimate about the population, we need to know something about the population. But if we knew something about the population, we wouldn't have to do any estimating. So how do we get around that? To overcome this problem, and I didn't write it in here, so I'm going to type it, of not knowing the standard error for the population, we can play some games with a sample. Now, what kind of games can we play? Well, let's pretend for a second, and I'm going to set up a quick example. Suppose we want to know the mean travel time for all commuters in, let's say, Dallas. Okay, I work for the city of Dallas. I work for traffic management. I'd like to kind of know how long on average it takes for everybody to get to work. So we need to know what we do with our infrastructure and our roads. If we want to know the mean travel time for all commuters in Dallas, it's not feasible to get measurements from all Dallas commuters. So we couldn't calculate the standard error for the population, much less the mean. The mean is really what we're interested in. So what's the standard go-to in statistics when you want to know something about a population, but you can't find it because for whatever reason, the standard go-to is we take a sample. So we take a sample. That sample has a mean and a standard error. But how can we estimate the standard error for the population based on that sample? How could we estimate the standard error for the population based on that sample? Well, we could just use the quote unquote best estimate approach. The best estimate approach says, well, whatever we get from our sample, we'll just assume it's the same for the population. But that's kind of an easy cop-out. Just whatever the sample says. So if the sample average is 10, we say the population average is 10. Well, no, I'd like something a little bit better than that. If our sample standard error is 0.5, then we'll just assume that our population standard error is 0.5. Well, to be honest, that's actually a bad idea too. It's even worse than using the sample mean to estimate population mean. So how can we do this? How can we estimate the standard error for the population based on that sample? And really, scratch that thought, based on that sample. And the answer is to do something called a bootstrap sampling. And I'll elaborate on what bootstrap sampling is in the next page on the Zoom session. But here's the basic idea. Let's pretend that we pick a representative sample of 50 Dallas commuters. Okay, let's pretend it's y'all. There's not 50 of you, but let's just pretend they are. We could measure y'all's mean, y'all standard error, and now we've got the results for a single sample. But samples change when you pick a different one. And so if I picked a different sample, it would have a different mean, different standard error. So ideally, it would be a good idea if we could pick multiple samples of a certain size. So let's not just pick one sample of size 50. Let's pick a bunch of samples of size 50. But let's say that we don't want to pick another sample of 50 and another sample of 50. We just want this one sample of 50 to try to represent multiple samples. Here's where the bootstrapping comes in. And I'll be honest, I don't know why it's called bootstrapping. The idea is this. Estimating is better when we can pick multiple samples of the same size. You pick a sample of 50, 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 everybody pick a sample of 50, everybody calculate a mean. Look at all these means. Let's make a dot plot. But it's also not feasible to pick 10 samples of 50, 100 samples of 50, 1,000 samples of 50, 10,000 samples of 50. And if you think I'm exaggerating, I'm not. 10,000 samples is usually the minimum. It's not impossible to discuss 100,000 samples of size 50. Whoa, whoa, whoa. If you're taking 100,000 samples of size 50, if you multiply, that's 5 million people. Are you asking me to sample from pick 5 million people? No, I'm not. Here's the trick. The idea is this: estimating is better when we can pick multiple samples of the same size. For example, if we could pick we'll just say 1,000 samples of size n equals 50 and calculate the sample mean for all of those samples. Let that sink in. 1,000 samples, size 50. Each one produces an X bar. We put them all in a dot plot and we look at the shape. If we could do that, then we could get a really good picture of the sampling distribution for the sample mean. And we haven't talked about the sampling distribution for the sample mean a whole lot, but that phrase, and I'm going to highlight it just for a second so you see where I'm talking about. That phrase, sampling distribution for the sample mean, means if we picked every sample of size 50 out of 1 million people, there's not enough time left in the universe to do that. There's so many such samples. But if we did, if we picked every single sample of size 50, calculated their X bars and made a dot plot for those X bar values, that's the sampling distribution for the sample mean. Of course, that's not very practical. Plus, picking 1,000 samples of size 50 means that we need at least 50,000 things to select from. Some populations aren't even that large. If they weren't, then we can measure them accurately. So how do we overcome this? This is impractical. So instead, here's what we do. Number one, pick a sample of a given size. In this case, for example, let's say n equals 50. All right, we're going to pick 50 commuters. Okay. From this sample, we can pick more samples of the same size. And you may be wondering, how is that possible? If I got 50 people in a room, let's pretend there's 50 of you. And I say, well, let's pick 50 of you. Okay, that would be all of us. Cool. I take your measurements. I calculated sample mean. All right, now let's pick another group of 50. And you're all looking at each other like, there's still only 50 of us, so you're going to pick us again? I'm like, well, no, because I'm going to get the exact same result. So how can we pick more samples of the same size? In other words, how can we pick more samples of 50 from a group of 50? And the answer is we can pick more samples of the same size if we sample with replacement. Now, what does that mean? That means if I pick one of you to be in a sample, then I can put you back with everybody and possibly pick you again. You can do that? Sure, we could. Why can we do that? Well, the reason we can do that, why can we do this? If our sample is truly representative, that was supposed to say representative, and random, then think of it this way. If this group of 50, and I'm pretending it's y'all, even though there's not 50, if you guys are truly a random representative sample of a population, that means that for each of you, like Priya, there are other people in the population that have the same value as her, whatever it is we're measuring. So for example, if we're measuring time to get to school and Priya says 20 minutes, then if this is a representative sample, then she is representative of other people in the population with the same answer, as are all of you. So if I say, let's pick 50 people, I pick Priya, write down her answer, put her back in the group, and then select another person at random, I might possibly pick her again. But that's okay, because there are other people out in the population that have the same measurement as her. So that's what sampling with replacement means. That means, well, does anybody here play Scrabble or ever played Scrabble? So it's your turn. What do? You draw letters out of the bag, right? Okay, you play a word, you draw letters out of the bag. That's sampling without replacement, because when you take the letter out, you don't put it back in the bag, do you? But what if you drew 7 letters, wrote them down, and then put the tiles back in the bag? That would be with replacement. I've replaced the tiles back in the bag. They can be selected again. You guys are like Scrabble tiles, except when I pull you out and write down your value, I put you back in the bag and you can get selected again. That's called bootstrap sampling. And again, I'm not 100% sure why it's called bootstrap sampling. If anybody wants to go off on a mental tangent and search it and find out and text me the answer, that would be cool. You know, if for some reason my voice is putting you to sleep, it could. But yeah, I'd kind of like to know, because when I have the available time, I probably won't ponder that question. So, you know, if somebody else does and sends the answer to me, that would be awesome. I did read the section. I couldn't find an answer in there. All right, so back to the task. Why can we do this? If our sample is truly random, representative and random, then each member of the sample represents multiple members of the population that could be selected in addition to the person in the sample. I'm not sure if that is exactly the way I wanted to word that. If our sample is truly representative and random, then each member of the sample represents multiple members of the population that could be selected in addition to the person in the sample. Yeah, that's what I mean. All right, so with this idea, we can actually pick as many samples as we want from a previously selected sample. All right, now, is this an easy thing to do? Of course not. Let's say there were 50 of you in here and I put all your names in a bag and I said, all right, I'm going to pick a sample of 50. Pull out a name, write it down, put it back in the bag. Pull out a name, write it down, put it back in the bag. Keep doing that until I get 50 of you. There's a sample. All right, let's do it again. Pull out a name, write it down, put the name back in the bag. Pull out a name, write it down, put the name back in the bag. I'm probably going to pick some people more than once per sample. Do that 50 times. Now I've got a second sample. Now let's do that 998 more times. You know, 100 years ago, this was a very theoretical concept that was very difficult to demonstrate. Not so much today. You know why? What do we have today that people didn't have 100 years ago? It's a lot of answers to that. You all have one with you right now, probably. A phone, computer, internet, shared knowledge across the world, things that can crunch numbers very, 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 very fast. In other words, technology. This is normally done with technology. Not too bad. I typed the word technology without looking at the keyboard. I could have done worse. I'm just curious. Does anybody in here actually know how to type by feel? Some of you do? Okay. I don't. I don't know if they actually teach that these days or if it's just something you pick up on. You know, back in the day, there used to be a class in high school called typing with a typewriter. Anyway, yeah, way back in the day. All right, so normally this is done with technology. Okay, so that's the idea behind bootstrap sampling. We can get a bunch of X bar values from a bunch of samples by starting with just a single sample. I want to demonstrate this on a very, very small scale, but I need something that will randomly pick numbers. Oh, this. Hey, Siri, pick a number from 1 to 10. A random
number between 1 and 10 is 8.
Couldn't you just say 8? Okay, so this thing will pick random numbers. So let's do a really small experiment. For example, from a population, we pick a sample of n equals 5 values. And our 5 values are as follows. Let's say we're trying to figure out how long it takes for people to get from to campus. For those of you who commute to campus, I'm just going to ask you to raise your hand if you drive here and just to estimate how long it takes you. So can anybody tell me? Yes, ma'am. An hour. So we'll say 60 minutes. Yes, ma'am. 40 minutes. Okay. Yes, sir. An hour. So we got another 60. Good. Yes, sir. 30 minutes. Okay. And I'm going to put my number in there, which is about 35. Yeah. Okay. So let's say that we have this and we want to do a bootstrap sampling. We're going to conduct a bootstrap distribution with, let's just say 4 samples chosen from this. Now, when you do a bootstrap distribution, or a sampling of it, I should say, you always have to pick the same number of values as there are in the sample. So we must always pick n equals 5 for our new samples. But when we pick a value, we can pick it again. We can pick it again in the future. Now, the problem is picking things at random. So I'm going to come up with sample 1, sample 2, sample 3, and sample 4. Okay, here's what I like for everybody to do right now. Okay. I want you to close your eyes because I don't want you to be influenced by anything you're looking at. And I want you to think of a number from 1 to 5. Just first number you think of, 1 through 5. Okay, you got a number? Open your eyes. Here's what I'm going to do. I'm just going to point at you. I want you to tell me what number you said. You know why they're giggling? Because I said pick a number from 1 to 5. Oh, that's okay. It happens. I've done much more egregious things than that, trust me. 2, second number in this list is 40. 4, fourth number in this list is 30. 4, fourth list in this number is 30. 2, second number in this list is 40. 3, third number in this list is 60. We just picked a bootstrap sample, and notice that we picked some of the values twice. We picked the 30 twice because 2 people said 4. I'm not done. We got 4 more samples. 3, 60. 4, 30. Anybody notice this is not being super random? Because there's 2 numbers nobody said. 4. Thank you. Even if you change your number. 4. Very popular number. 3. Y'all know what I'm doing. I'm typing the first, second, third, fourth, or fifth number as you say these numbers. 5. Thank you. 3. 3. Okay. Now look at all the 60s we picked. We picked 3 60s, but that's okay because the 2 of you that said 3 would represent other people in the population with the same value as you. All right, I'm just going to pick something at random here. The square root of 2 is 1.4142. All right. So I know that wasn't very random, but it's just the first 5 digits in the square root of 2. Yeah, that was super nerdy way to pick random numbers. All right, so it's okay when you're doing a bootstrap distribution, when you're doing bootstrap sampling, to pick a value more than once from your sample, because that sample, if it's representative of the population and random, each value in there is probably the same as other people in the population. So it's okay to select it more than once. Now, each one of these has an X bar. I'm going to need your assistance. Listen very closely. On this side of the room, females, however you want to define that, I would like for you to find the average of this first sample. This side of the room, males, so Gabe, I need you to find the mean of the second sample, okay? The mean of the second sample. This side of the room, females, mean of the third sample. That side of the room, males, mean of the fourth sample. And if you don't know which one I said, just pick one and find its average. You don't know how to find the mean of 5 numbers, right? And Zoom folks, if you want to, just pick a sample and find its mean while I set up some X bars. Now, none of these should come out too bad. In fact, they all should come out to be whole numbers. Every one of these is divisible by 10, which means they're divisible by 5, which means when I add them, it's still divisible by 5. All right, ladies on this side, did anybody come up with the mean for the first sample? Exactly 40, okay. Gabe, did you get the second one? 48, okay. Ladies on this side, third one? 49, okay. Guys on this side, last one? 50, okay. Notice all of those are different. They should have been. They're all from different samples. So does this tell us anything about the population mean? It kind of tells us that it's probably somewhere between 40 and 50. Now, imagine doing this, well, I don't know, 99,996 more times. We're not, but imagine it. Then we would have 100,000 X bars that can make a dot plot. And from that dot plot, we could gather some information. We could look for the center, which is going to estimate the population mean, but we could also figure out the standard error based on how wide it is. I'll show you what I mean. Give me 1 second to come up with 99,909. No, I'm just kidding. Give me a second to show you some technology. Now, I haven't pulled up the technology yet, so I'm going to have to jump on the internet just for a second and go to StatKey. Now, I am not going to ask you to do anything in StatKey. I want to make that clear. Because even when we do this, we would not all get the same results. I went StatKey, I searched the first one. This is associated with the textbook. I'm going to sampling distribution for mean. Now, the problem with this one is, you know how in the book sometimes it says, here's some data sets from different whatevers. This sampling distribution for mean has data sets that you can select from. If we drop down, we'll see many, not all of them that are in the textbook, but for example, oh, that one's not in there. Let's just pick baseball player's salary in millions for the 3rd edition. We could look at the data set. I'm going to show it to you, but we're not going to write it all down. I know that's really hard to see, but it's a bunch of names and some numbers that represent the millions of dollars they earn per year. Max Scherzer, 42.143 million per year. Good for him. But let's say that we have, we want to pick a sample of a certain size. For example, let's say we want to pick 50 players and calculate their average. I can click this button that says generate one sample and it will do that. Okay, we picked 50 numbers from this sample and their mean was 4.649 because we're doing the mean. But if I wanted to do more samples, like 100, I could just click generate 100 samples. And now it just did what we did when I asked you to pick random numbers. It picked 50 samples Actually, this isn't quite bootstrapping, but the concept is the same. So I'm going to use this here. It picked 50 samples and calculated their X bars and dropped them there. Now, if we wanted 100,000 samples, I would have to click generate 1,000 samples 100 times. I'm not going to do that. I'm just going to click enough of it in order to make my point. Right now we're at 5,100. It says it right there, 5,100 samples. But it's like repeating what we just did. Right now we're at 6,100 times. Let's pick 6,100 samples of size 5. And if you notice, it's giving me some information about all these X bars from all these samples. Up here, it's got the mean of those X bars, and it's even got the standard error for them. So if we want to come up with a standard error for a sampling distribution, we can just use some technology. Now, for this one, unfortunately, we're limited in what we can do for means because it's requiring a data set. You can actually upload your own data file. In fact, I'm going to give that a try. I'm going to improvise this right before your very eyes. Times to travel. What were they, like 60? They were on here. 60, 40, 60, 30, and 35. 60, 40, 60, 30, and 35. I'll take that off. We're going to save this. Get rid of that. I'm going to save this as, we'll put it on the desktop because that's the easiest place for me to find things. We'll just call it times. And now I'm going to go back into the stat key, and I'm going to see if I can upload that real quick. Put it on the desktop. Times. There it is. Let's see if this works. Only text or CSV or TSV files can be uploaded. All right, I'm not going to waste any more time saving it as a CSV file. My point is you can upload your own files and do this as well, but we can also do it for proportions. Excuse me. For example, let's say, sorry, getting dry throat up here. Let's say that we wanted to know what proportion of all students like, I have no idea, Star Wars. I think that's something that's kind of polarized in people's views of it. Love it, hate it, or never seen it. And let's say that I ask 5 of you. I'm just going to ask the 5 people in the very back of the room. So Gabe and his band of 4 back there. All right, so just real quick. Do you like Star Wars? No? You? Yeah. No? Yeah? No? Gabe? Gabe, you like Star Wars? Do you like Star Wars? Yes. So it was no, no, yes, no, yes. All right. So I surveyed 5 of you, and these are the answers that I got. Okay. And by the way, we can calculate a p-hat value for this. If we wanted to measure how many of you said yes, what percent of them said yes? It should be kind of easy. It's 2 out of 5, 40%. So our p-hat for the sample was 40%. But the problem is it's one sample. So to say, well, based on you 5, 40% of the whole class like Star Wars. Probably not. If we did a bootstrap and we came up with, I don't know, 4 samples, I'm just going to, hey, Siri, give me a random number between 10,000 and 900. Shoot, shut up. Hey, Siri, give me a random number between 10,000 and 100,000.
A random number between 10,000 and 100,000 is 57,143.
Okay, don't ask me how I turned that number into that bootstrap sample. I basically went 1, 2, 3, 4, 5, and then I went 6, 7, 8, 9, 10 if it was bigger than 5. All right. Hey, Siri, give me a number between 10,000 and 99,000.
A random number between 0 and 100 is 59.
What the hell? Piece of garbage. All right. So anyway, if we pick samples at random, it might go yes, no, 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 yes, which mirrors exactly the sample that you saw there. It might go yes, yes, no, yes, yes. Because some of the yeses got picked more than once. It might go no, 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 yes, no. And again, I'm not randomly selecting these. I'm just sort of randomly writing yeses and nos. But if we did make a random selection from the original 5 answers, first, third, fourth, second answer, and then wrote down the results, we could get something like this. And maybe the no gets picked 5 times in a row. It could happen. Well, each one of these has a p-hat. Remember, p-hat is just what percent did something. In this case, the percent that said yes. 40% said yes there. In this one, it was 80%. In this one, it was 20%. And in this one, it was 0%. None of these randomly selected answers from the first group said yes. Can somebody do me a favor and average those 4 numbers? The 4% that we come up with. $35. Okay. So the mean of those p-hats is 35%. And there's something that I forgot to do on the last one, and that was to come up with the mean of the x-bars. But where we're going with this, and I do have a point, is if we did a bootstrap sampling of these results, no, no, yes, no, yes, with as many samples as we could of the same size, that's why all of them have 5, then each one of them would have a sample measurement, in this case, p-hat, and we could take their average, and that would, this number down here, the more times we do these bootstrap samples, the closer that number gets to the proportion for the population, assuming that everything is random and representative. I want to go back to the travel time one again, real quick. I forgot to follow it up with what's the average of all of our x-bars. I don't know what the average of all of the x-bars is. So it's just the sum of those numbers divided by 4. 120, 170, 187 divided by 4 is
46.75.
I was going to say 46.75, and that was actually whispered in my ear too. It's actually not very much of a whisper. I should probably turn the volume down. 46.75. Yes, oui, n'est-ce pas? Est-ce verdad? Si. Okay, so what we would say is, based on our bootstrap sampling distribution of only 4 samples, we would say that the mean of all the x-bars is 46 points, mean of all these x-bars. And what this tells us is, so we estimate that the population mean is about 46.75. And the theory is, if we repeated this process of picking a bootstrap sample, meaning we can sample with replacement, cranking out more and more and more samples and generate more and more and more x-bars, then the mean of all those x-bars gets closer to the population mean. So we can do a pretty bang up job of estimating something about a population, even with a fairly small sample, if we do a bootstrap distribution. I want to go back to the one about the Star Wars and the proportions. The mean of these p-hats, and as a consequence, we can estimate that the population proportion, because remember the p-hats are sample proportions, is about 35%. Now that's probably not a very good estimate because we only took 4 samples, but if we took, say, 100,000 samples, then the average of the p-hats from the samples would be a tighter and closer estimate of the population proportion. All right, so does anybody have any questions about what I mean if we repeat this over and over and measure all of them and average their measurements, we get closer to the actual population value? Okay, last thing in this section, because we're getting close to the end of the time. All right, the mean of all these sample measurements, whether they're x-bars or p-hats or whatever it is we're measuring from each sample, only gives us a quote best estimate for the population value. And when I say best estimate here, what I really mean is a single number. It would be better if we could come up with an interval of values. So here's where this concludes. From all of the sample measurements, so all the X bars or all the P hats or whatever it is we're measuring, we can calculate, and when I say we, I mean technology, except I can't spell calculate. We can calculate. From all the sample measurements, we can calculate their standard error. Okay. And if the distribution of all these sample measurements is approximately bell-shaped, give you a second to get caught up there. If the distribution of all the sample measures is approximately bell-shaped, and that is grammatically correct, the distribution is approximately bell-shaped, and there's a comma after that. And just to remind you, we've already seen this phenomenon. I'm going to switch back over to the stat key for a second. Look at all them dots stacked on top of each other in a dot plot. It's pretty bell-shaped. It's not perfect. It's not smooth. It'll never be perfectly smooth. That would require an infinite number of dots. And frankly, I don't have that kind of time. But if it's approximately bell-shaped, and you can achieve that if you get enough samples. Back to this. If the distribution of all sample means, if all sample measures is approximately bell-shaped, and this will happen with enough samples. So it's not a question of if, it's a question of when. And this will happen with enough samples. Then we can construct a 95% confidence interval using the mean of all the sample values as the center and their standard error to calculate the margin of error. Want to remind you that if we know the center and we know the standard error and we know approximately bell-shaped, that's kind of important, then that's the formula for the 95% confidence interval. So that's one place we can get the standard error from technology with enough bootstrapping samples to generate a good center and a good standard error. I'm going to do a follow-up with the dot plot that we have in StatKey to show you how that technology gives us the information we need to construct a 95% confidence interval. I'll come back to the screen in just a second. I want to switch back over to the sampling distribution that we did here. It's in very small font size, and you may not be able to see it from where you are sitting, but whatever these numbers came from, they were salaries of baseball players in millions. Oh, and I just realized something. Notice when I float around, it stops at a sample, but over here, I got to move it over here on the right, it tells me, all right, for that sample, this is its mean, this is its median, this is its standard deviation, but the numbers I'm interested in are in the upper right corner. I'm going to try to zoom in on this to see if you can see those numbers or if it's just going to keep the font size the same. Yeah, that's not working. This font size stays exactly the same. Let me take it back down and try one more trick. There we go. It tells us, hey, you took 6,100 samples. The mean of their X bars in this case was 5. I'm not sure what happened there. I killed it. kill you. The mean was 5.407 for all of their X bars, and the standard error for all of their X bars was 0.868. That can be used to construct a 95% confidence interval for the population mean. You would take that mean as the center, do plus or minus the standard error. Can somebody do me a favor and write down that mean and standard error? I'm afraid when I click this, I'm going to lose it. Anybody got it written down? Good. Okay. I'm going to click wait and hope that it stops being itself, but we'll go back here so it won't matter anyway. All right. So to wrap up this discussion, in the bootstrap distribution we did in StatKey, the mean of all 6,100 sample means was 4 point what? I'm sorry, louder. 507, thank you. I only got one ear working, the other one's doing this. The mean was that with a standard error of 0.868, okay. Since the distribution was approximately bell-shaped, I keep wanting to say approximately normal, but we haven't formally introduced that word yet. Approximately bell-shaped, the 95% confidence interval for the population mean is, time to draw. Draw. 4.507 plus or minus 2 times 0.868. I need everybody to do me a favor, either pick the plus or pick the minus and figure out its answer. In a minute, I'm going to ask you the answer for the minus, and then I'm going to ask you the answer for the plus. Raise a hand if you have either. The answer to that plus 2 standard errors or that minus 2 standard errors. Anybody have the answer to either? Gabe, which one you got? 6.243. Okay. Does anybody have the answer to the minus? I'm going to assume these are correct unless anybody wants to take them to task. So here's what we know. Based on our sampling distribution, our bootstrap distribution, we can say with 95% confidence that the mean salary for all baseball players is between 3.639 million and 6.243 million. Now, granted, this was 100% based on the sample selected. So from a different sample, we might get a different result, but it's not too shabby. All right. So it was a lot to do to say the following. I'm not going to ask you to get in StatKey. What I'm going to ask you to do is this. If you have a center and a standard error, be able to do that, which is the same thing we did last time. Yes, sir. Which one? The from? Oh, controversy. What was it? Is that better? Thank you for not letting me get away with that. Or rather, I should say, I don't remember who gave me that one, but it was 2.771. All right, I'm going to pick an assignment. Keep an eye on Canvas for it. You don't have to hang around to wait for it. I am going to pick it right now, though, if you want to wait. All right, thank you for your time. Keep an eye on Canvas for what I want you to do on Monday. Basically, it'll be watch videos. Okay? All right, and folks on Zoom, if you have any questions, feel free to drop them in the chat or unmute your microphone because I am listening. Otherwise, thank you for attending. And I will be saving the Zoom session to post on Canvas. It is. It's actually 1.96.